Alrighty, hello and welcome to lecture. Again, thank you, everybody, for your understanding and flexibility. Tonight, meeting at an unconventional time. Um, I so appreciate it, and also the emails you sent as well. Really appreciate it. All right, so we are going to be finishing up um, chapter 7 and starting chapter 8. We just have one last thing to talk about in chapter 7. Um, and that topic is osmosis. We're going to touch on it briefly and then dive into chapter 8 material. Again, we're just going to take a moment. All right, so osmosis. Um, Osmosis is a word that when you hear it, you first think about sleeping with your textbooks under your pillow to absorb the information magically through osmosis, right? That's at least the first thing that comes to mind when I hear the word. And unfortunately, that is not how osmosis works, but it does that idea of like putting it against yourself and having the information flow into your brain actually isn't a bad starting point for talking about osmosis. Now, osmosis is a process that occurs um, when you have two solutions with different concentrations in contact with each other through what's called a semi-permeable membrane. So, oops, let's not start out pink, let's start out. So if we have a, actually, I'm going to make this a different color. So we have two solutions here. All right, start a little lower. So separated by a barrier, and let's say we have solute particles in solution. All right, and we have one solution, the solution on the right has a very high concentration, the solution on the left has, as you can see, a much lower concentration of solute particles. Now, this barrier separating the two solutions, this is called a semi-permeable membrane. And what we mean here by semi-permeable membrane is it's a barrier that some things can pass through and other things can't. Specifically, the semi-permeable membrane allows solvent molecules to pass back and forth, but prevents the solute from flowing back and forth. Right? So solvent can go back and forth, but solute can't. Now, osmosis. Excuse me. Actually, I did this in the wrong layer. I actually want to do this down here. Now, the process of osmosis, or I should say, what happens in osmosis is since the solvent is allowed to flow freely back and forth, it will do so until the concentration of solute on both sides are equal. All right. So osmosis is a process that just happens in nature, and what'll occur is the solvent will flow away from the less concentrated side towards the more concentrated side until the concentrations on both sides are equal. So what happens once the process of osmosis is complete is you will have a much lower solvent level on one side, a much higher solvent level on the other. And it does this so that the concentration on both sides of the semipermeable membrane is the same. All right, and that's why the joke about sleeping with your textbook under your pillow the night before an exam is an osmosis joke, because all the information on the exam is in your textbook, none of it's in your brain, and so the process of osmosis should result in the flow of information so that the amount of in your brain equals the amount in your textbook, and now you actually understand the joke, if you didn't already. All right, so that is the process of osmosis. Now, when I say that the concentrations are equal, I'm for osmosis considerations. It's not the concentration of any given compound; it's the total concentration of particles. All right. So, for example, and this will tie into a little bit what we were discussing last lecture. When we talk about concentration for the process of osmosis, this will relate to the Van Hoff factor from freezing point depression, you'll see. Let's say we have a 1.0 molar solution of sodium chloride. Well, that means we have 1 mole of per liter of sodium chloride molecules. But the thing is, as we were talking about last lecture, aqueous sodium chloride has a Van Hoff factor of 2 because it actually has 2 distinct particles dissolved in solution, right? So here, because 1 molecule of sodium chloride actually has 2 distinct ions in solution, we say that the Van Hoff factor is 2. And you have to take the Van Hoff factor into account when you're calculating concentrations for the process of osmosis, all right? And the unit that we use is something called osmolarity. Abbreviated osmol. And osmolarity is equal to the molarity of a solution times its Van Hoff factor. So, for example, a 1 molar solution of sodium chloride would actually have an osmolarity of 2.0. Because again, our Van Hoff factor for sodium chloride is 2. All right, so another example. If I asked you to determine the osmolarity of 2.33 molar 2.33 molar solution of aqueous calcium chloride, we know that the osmolarity is equal to the molarity times the Van Hoff factor. So we need to determine our Van Hoff factor of calcium chloride. And you can see that when you look, at how many particles calcium chloride will break up into, you'll have 1 calcium ion and 2 chloride ions. So our Van Hoff factor here is 1 plus 2 or 3. So the osmolarity of 2.33 molar calcium chloride is 2.33 times 3, which if you can do that in your head, that's awesome. Wait, it's going to be 6.99, I think. Let's find out. 2.33 times 3 is 6.99. So we would say that this solution has 6.99 osmolarity. Because again, the process of osmosis is not concerned about the concentration of individual molecules, it's concerned with the concentration of products, or not of products, of particles. There we go. All right. So the process of osmosis is why you can't drink ocean water. It's why you can't drink salt water. The reason why is because is sig figs required? Yes. Great question. Sig figs are totally required. But the thing you have to remember is that your Van Hoff factor, this thing right here, is not measured. Let me give myself a little bit more room here. There we go. This is not measured, so it will not limit your sig fig. So when it comes to determining how many significant figures we should have, we start with 3, so we have to end with 3. So 3 sig figs is the correct number of sig figs. Great question, though. So, yes, yeah, totally. See, the thing is, if that 3 were a measured quantity, it would only have 1, and so it would limit us. But because it's not measured, we didn't actually measure it. It's just the number of particles in 1 molecule of calcium chloride. It's an exact number. So osmosis is why you can't drink salt water, can't drink ocean water, because the concentration of solute particles in ocean water is greater than the concentration in your sorry. The osmolarity of ocean water is higher than the osmolarity of your blood cells. So what will happen is when you drink it, because the concentration of that ocean water is higher, your blood cells will deflate. They'll go flat because all the solvent will flow out of the blood cells into your bloodstream, which is where the salt water ends up. Daisy, yes. You always want to do sig figs. Always apply the rules for sig figs for every problem. That is 100% correct. Osmosis is also why you can't drink large amounts of just pure distilled water, because distilled water has no solutes in it, has no solutes, and so the particle concentration inside your blood cells is higher than that of distilled water, so solvent will flow into your blood cells until they swell and burst. So you actually need to drink water that has just the right amount of minerals, a near match to that of your cells. All right, and there are, when you talk about osmosis and your body, there are 3 types of solutions that you need to be aware of. An isotonic solution is a solution with the same osmolarity as blood. All right, you have the same osmolarity as your blood cells in an isotonic solution. A hypotonic solution is a solution with a lower osmolarity um, than uh, than your blood cells. I should say blood cells. All right. So if you ingest a hypotonic solution, which has a lower osmolarity than your blood cells, solvent will flow from your bloodstream into your blood cells, causing them to inflate or possibly burst. So I'm going to need to lower this down just a bit. So it causes blood cells to inflate and or burst. All right, and then finally there is the last type of solution is called a hypertonic solution. Which has a solution with a higher osmolarity than blood cells. And this will cause your blood cells, to deflate. All right. So that is the end of chapter 7. Let me switch over my notes and we'll dive in to chapter 8. All right. So chapter 8 might be the single coolest chapter in this book, if you were to ask me. In this chapter, we are going to study reaction rates and chemical equilibria. Our discussion of the first is going to naturally flow into a discussion of the latter. So let's dive right in with a discussion of reaction rates, and every discussion of the rate of reaction begins with an introduction to collision theory. All right. And real quick, just so you know, when I talk about reaction rates, I'm talking about rates as in speed, not cost. So we're talking about the speed at which chemical reactions. Oh, rocks, this is going to be fun. It so totally will be. So reaction rates, we're talking about the speed at which chemical reactions proceed from reactants to products. All right, that's what we're talking about. We're talking about how fast reactions go, what affects the speeds, because some reactions are lightning fast, right? You light a piece of paper on fire, it proceeds fairly quickly. Some reactions are very slow. For example, iron rusting, like a bridge rusting. Iron oxidizes at an appreciable rate. It can be measured, but it's a slow one. It's not instant like combustion of paper. So different reactions have different speeds, and we're going to start digging into that phenomenon. Another name for this field is chemical kinetics. All right. So collision theory starts from a very simple premise. All right. And that premise is reactions occur when reactants collide. All right? That is the premise of collision theory. And when you think about it, it really makes sense on a first principles level. If you consider, for example, the chemical reaction between solid calcium and chlorine gas that forms the ionic compound calcium chloride. So this is a combination reaction, example of a combination reaction. It's not possible for this reaction to take place unless our chlorine comes into physical contact with our calcium, right? What has to happen here for this reaction to occur? We have calcium hanging out with its 2 electrons. We have our molecule of Cl2, which is covalently bonded. And calcium's a solid, chlorine's a gas. If these particles do not collide, no reaction will occur. They have to get close enough to break bonds and form bonds, right? They need to actually smack into each other. For that reaction to take place, for calcium chloride, the ionic compound, to actually form. There's one chloride, here's the second. All right, so it makes sense so far. There's a catch, though. You're like, why doesn't it just happen? Well, one, chlorine's in the gas phase, calcium's a solid, so we actually have to wait for a chlorine molecule to ricochet off the solid surface for that reaction to happen. But there's a second problem. The problem is right here, and it's here, and it's here, and it's here. What am I doing? I'm highlighting all the electrons. And electrons repel other electrons. Why? Well, it's simple. They're negatively charged. And we know that like charges repel each other. So there's before the reaction can happen, your two particles have to collide, but the closer they get, the closer their electrons come to being in contact, and the more the electrons repel each other, all right? And this phenomenon, the fact that electrons repel each other, is why every reaction has what we call an activation energy. Or a barrier to activation. There, you have to overcome the fact that these electrons do not want to touch so bad. You have to put in enough energy to overcome that repulsion in order for the reaction to take place. This is true for every chemical reaction. All right? Now, if we were to graph this, so, oops, that's ugly. That's better. So I'm going to put energy on on my y-axis. On my x-axis, I'm going to put something called the reaction coordinate. One way you can think of it is of the reaction coordinate is it's kind of like time. All right, for this type of graph, which is called a reaction coordinate diagram, there it's right on the x-axis. As you're close to the origin, this is where your reactants are. And then as you move along the x-axis, your reactants become your products. All right, so this is mapping the energy, how energy changes as you move from the reactants to your products. And what you'll see is as you have two reactants, we're getting closer to reacting. That means they're approaching their collision. The closer they get, the closer they approach their collision, the higher the energy gets until you hit a relative maximum, and then the energy drops off, all right? At the relative maximum of your reaction coordinate diagram, right here, this is where the collision happens, all right? That is where your reactants actually connect, collide, to react, to transform into our products, all right? And the barrier to activation, the activation energy, can be measured on this graph because it is the difference. I'm actually going to pick a different color there. Let's go with something a little more contrasting. The barrier to activation can be measured as the distance between the energy level of the reactants and the energy level of that relative maximum where your reactants collide. So this is our EA, and EA is our energy of activation. That's not the only thing we get off of this graph. If you measure the difference between the reactants energy level, where the reactants are and where the products are, this will give you, you can see that here for this graph, the products are lower, and this is the energy released by the chemical reaction. because your products are lower in energy than your reactants. You started up here, you're ending down here. Energy is released, and that means that this reaction is exergonic. Another way to think of this is you could think of it as exothermic. Technically, those are two different things, but they're very closely related. So if remembering that exergonic is exothermic, which is the release of energy, if you find that helpful, roll with it. And for exergonic reactions, that means energy is released by the reaction. So combustion is an example of an exergonic reaction, where you're releasing energy into the environment in the form of light, in the form of heat, at the same time. Now, you might be going, well, wait a minute, Josh. I know that some chemical reactions release energy, but every chemical reaction doesn't. So what happens if energy isn't released by a chemical process? What happens if energy is absorbed? And I'm so glad you asked, or I guess I asked, because that's where we're going next. But real quick, we got a question in the chat. Is there ever some sort of mutation where two electrons don't reach the peak? Rox, that is an interesting question. So the question is there ever a situation where you don't actually reach this crest right here, where you're gaining in energy, right? They're approaching a collision, but then they miss and they fall back down. They don't quite reach that. That happens all the time. That's actually happening as we speak. So think about this scenario. And actually, before I give this example, let me just say, when that happens, that just means no reaction occurs. For a chemical reaction to occur, you have to get that collision. You have to actually make it and overcome your activation energy. If you don't, no reaction occurs. This is happening as we speak right now, and it's something I'm very thankful for. So let me ask you a question. Does hair burn? Can you burn hair? The answer is yes, right? It doesn't smell very good when it does, but you can light hair on fire. That's a thing you can do. What is hair reacting with when it burns? It's reacting with oxygen. Now think about this. There's oxygen in the air we breathe. So surrounded by oxygen, all of us have hair on our heads. Why isn't our hair on fire? The answer to that question is there is not enough energy in the rooms that we're sitting in for the reaction between hair and oxygen to overcome the activation energy. So literally every moment of our lives, Rox, that scenario you asked about is happening because there's oxygen in the atmosphere. Oxygen's getting close to our hair, bouncing around, swirling around our hair, but there's not enough energy in the room to overcome the barrier of activation to start the combustion reaction between oxygen gas and hair. Thank goodness. Otherwise, we would be much shorter lived as creatures. So that happens all the time, fortunately for us. That when you don't have enough energy to get over that barrier, no reaction will happen. And the reactions will just slosh around waiting for there to be enough energy so that they can. Often you'll see chemical reactions where you have to add heat for the reaction to start taking place. And that's because of this phenomenon. Rox, excellent question. Okay. So This is a, so I guess before moving on, let me just tie this up. So this whole graph is called a reaction coordinate diagram. I don't know why I put an E on the end of diagram. All right, so this is a reaction coordinate diagram. Thank you. And this is a reaction coordinate diagram for an exergonic reaction, right? For a reaction where energy is released. What about chemical reactions where energy is not released? What do those look like? And as you'll see, they're similar. There's one key difference. So we have energy on the y-axis. We have our reaction coordinates on the x-axis. And we know as we're close to the origin, we have our reactants. And then as you move away from the origin, eventually your reactants become your products. All right? Now, for the actual reaction coordinates, we know we have to overcome our energy of activation, as always, right? And we know that the energy of activation is the distance between the collision and the energy level of your reactants. All right, so there's the barrier of activation. We also know that the energy absorbed or released by the reaction is the energy difference between the reactants and the products. Now, when energy was released for an exergonic reaction, we saw that the products were lower in energy, at a lower energy than where the reactants started. Here you see the reverse is true, that the reactants are lower in energy and the products are higher. So we've actually gone up in energy as we've gone transformed from reactants into products. So here energy is absorbed. Energy is absorbed. This is an endergonic reaction. Which, if it helps you to think about it, you can think of it as an endothermic reaction. Again, technically different, but the two are very closely related. All right, so we have endergonic, energy is absorbed. Exergonic, energy is released. All right, and the key difference between the two is the energy, well, the energy level of the product. So let's just do a summary here. Between exergonic and endergonic. For an exergonic reaction, energy is released. For an endergonic reaction, energy is absorbed. All right. One way you can spot an exergonic reaction is the energy of the reactants will be higher, i.e. greater, than the energy of the products. For an endergonic reaction, the opposite is true. The energy of the reactants will be lower than the energy of the products. All right? Because you've gained energy. The last key difference, and this is a new way of kind of putting it, is with an exergonic reaction, you have, if you look at a balanced chemical equation, you've got your reactants becoming products. Heat or energy is going to be, because it's being released, energy can be considered a product of this reaction. All right? Energy is produced by, released by exergonic processes. The opposite is true for endergonic reactions. For endergonic reactions, energy, because it's absorbed, can be considered a reactant as a component of the reaction needed to get to the desired product. All right, so this is kind of the difference, the breakdown between endergonic reactions and exergonic reactions. All right, now, that was a little thermodynamic interlude. Let's focus on rates. Okay, so why did we introduce this? Obviously, collision theory, we know that reactions have to collide in order to occur. But what does that mean in the context with the focus of this chapter being reaction rates? Well, first and foremost, oops, open a new slide here. First and foremost, the energy of activation determines the reaction rate. All right? The energy of activation determines the reaction rate. If the energy of activation is large, that means the rate, the reaction rate, is slow. Which makes sense, right? If it takes a ton of energy to go from reactants to products, then you've got to amass that energy to push your reactants towards products. That's going to take more time. The flip is also true. If the energy of activation is small, then the reaction rate is fast. All right? So if the barrier of activation is low, then it doesn't take much effort to get over that barrier at all. The reaction is going to proceed very, very quickly. This is why, well, actually, I'm gonna wait to say that. So, what are so that's one feature of a reaction coordinate diagram with a direct influence on, and it's the key determining factor for reaction rates, how fast reactions will go. But there are also, in addition, so you can't change the barrier of activation. I'm going to show you one way you can actually in a few minutes, but for now I'm just going to say you can't change it, and then I'll contradict myself later. But there are factors under your direct control that will influence how quickly or slowly a reaction proceeds. And here's the way to think about it. Again, collision theory. When two reactants collide, that provides an opportunity for them to react and form products, right? So here's the key thing you want to keep on the forefront of your mind as we move through these next few examples. Anything that increases the number of collisions will increase the reaction rate. Anything that increases the number of collisions will increase the reaction rate. All right, so let's think about what we can do to increase the number of collisions. The first place I'd like to draw your attention is that of concentration. Higher concentration means that you have a higher density of particles. So if you have a higher concentration, you're going to have more collisions. If you have more collisions, that's going to increase your rate. So higher concentration increases, oops, want that in black. Increases collisions. Which increases reaction rates. The opposite is true of low concentrations. Low concentrations decrease the chances of particles colliding. That is going to slow your reaction down. But high concentration increases the rate of reaction. All right. Temperature can also influence reaction rates. Oops, sorry about that. So higher temperature higher temperatures mean that particles are moving faster than they would be at lower temperatures. And this increase in motion will lead to more collisions. Oops. So higher temperatures whoops. Increases motion, I should say particle motion, which increases collisions, which in turn increases reaction rates. All right. All right, now finally, there's one last thing that we're going to talk about that affects the rate of reactions, and that is the presence of catalysts. Now, catalysts affect reaction rates, but they do so in a way that's so all of the means we've been looking at for increasing our reaction rates up to this moment have just been like increase the number of collisions. If you can get more collisions, you get a faster reaction. Catalysts do increase reaction rates, but they do so operating at a fundamentally different capacity. So we're kind of going to give them their own little category here. So catalysts do increase the rate of reactions. They increase reaction rates by providing an alternate reaction with a lower energy of activation that still makes the same products from the same reactant. All right, that is what a catalyst does. What are we talking about? Well, let's draw a reaction coordinate diagram. All right, so let's look at a reaction. I'm going to draw an exergonic reaction here. So here's our reactants. Here's our products. And here's our reaction coordinates. This is our EA. Now, what a catalyst does, all right, now a catalyst provides a different reaction pathway that will make the same product from the same reactant. So adding a catalyst, it's like doing this. It's technically a different reaction, but it's strikingly similar because it makes the same product from the same reactant. And if you compare the energy of activation for the catalyzed reaction versus the uncatalyzed, so let me just label my legend here. So this is no catalyst, the uncatalyzed reaction versus the catalyzed reaction. You can see that the catalyzed reaction has a lower energy of activation, which means it's faster. You start with the same product, you start with the same reactant, you end with the same product. The catalyzed pathway has a lower energy of activation, so it will have a faster reaction. Yeah, exactly. They're like fraternal twins, where one is Arnold Schwarzenegger and one is Danny DeVito. All right, so that is how catalysts increase reaction rates. They don't do it by increasing collisions. So all the same things can apply. High concentration, raise the temperature, all that stuff will increase your reaction rate. But the way catalysts increase the reaction rate is providing an alternate pathway with a lower energy of activation. All right. So this lecture so far has been very kind of dialogue heavy. There haven't been a ton of examples of problems to break out and work. And this part has been largely conceptual. So, you know, with this stuff, I could ask you which one would be faster and show you two different energies of activations, one large, one small, that sort of thing. Or ask you about increasing temperature or increasing concentration, that sort of thing. We're about to move to a part that will be more applicable to doing examples. We may not get to a ton tonight, but we're about to shift from talking about the rates of reactions to something called chemical equilibrium. This part can be conceptually challenging, so if you find this to be harder than normal to wrap your mind around, you're not alone. I definitely recommend rewatching lecture, looking at reading the book, even bringing me questions and officers. We can get into it a little more if you struggle with this this material. All right, chemical equilibrium. So to begin our discussion of chemical equilibrium, I want you to consider two chemical reactions. The first is a combination reaction. All right, consider the combination reaction between hydrogen and iodide to produce hydroiodic acid, HI. All right, there's a combination reaction. Now, let's consider a decomposition. A decomposition reaction between, well, not between actually. Decomposition is you start with something and it falls apart, right? So consider the decomposition of hydroiodic acid. When hydroiodic acid decomposes into its constituent elements, it falls apart into hydrogen and iodine. All right. Do you notice something weird? Do you notice that the reactants of our decomposition reaction are the products of our combination reaction? And did you notice that the products of your decomposition reaction are the reactants of your combination reaction? These two reactions are like mirror images of each other, right? It's like one undoes the progress that the other one accomplishes. And this may leave you wondering which one occurs. Does the first combination reaction happen, or is it the decomposition reaction that happens? Which one is the one that's real? And the answer to that question is they both are. They both occur. This is an example of something called, yeah, Rock's exactly, it's flip-flopped, a reversible reaction. A reversible reaction. It's one in which both are operative, both are happening simultaneously. And the way we show this, the way we depict it, is we write it like so. We write, H2 plus I2 produces 2HI. But to show that the opposite process is also happening, you draw an arrow, just like we drew an arrow going from the reactant side to the product side, you draw an arrow going from the product side to the reactant side, because that second reaction is also simultaneously occurring, all right? And we call, there's just a little bit of nomenclature. We call this the forward reaction. The forward reaction is the one where your reactants are on the left and your products are on the right. The reaction where that's going the other direction, we call the reverse reaction. It's called the reverse reaction because the reactants are on the normal product side and the products on the normal reactant side. All right, so when we talk about the forward reaction, we're talking about these two producing this guy, and when we talk about the reverse reaction, we're talking about these two producing these guys. All right, so that's the forward and reverse reaction. Now, I want you to take a moment and consider this reversible reaction. H2 plus I2 reversibly producing HI. And I'm going to make a graph here. Let's construct a graph. Actually, a new kind of graph, one that plots reaction rate, so how fast a reaction is going, on the y-axis, and time on the x-axis. All right, and the forward reaction rates, I'm going to color orange, and the reverse reaction rates I'm going to color this green. All right. Now, I want you to think of the rates of these two reactions. The second you mix your reactants together, right? That split second, H and I are mixed, but they haven't yet had a chance to react yet. The concentration of your reverse reaction at that time zero, the concentrations are zero of HI. No HI has formed. Which means if there is a concentration of zero, if there is no HI, then there's no reaction rate. Its reaction rate must be zero. You have to have some HI for the reverse reaction to have a speed, but no HI is formed yet. So the initial reaction rate of HI is zero, and the reaction rate for the forward reaction rate is going to be something. I'm not going to put a number on it, but it's going to be some non-zero number. Now let's say a little bit of time has passed. Think with me, we're doing a thought experiment here. After a little bit of time, the concentration of H2 and I2 has decreased. All right? It's decreased because they've reacted and become HI. Since H2 and I2 have reacted away, their concentrations have decreased, and at a lower concentration, that means you're going to have a lower reaction rate. Now that a little bit of H2 and I2 have reacted to become HI, now that we have a concentration of HI, its reaction rate has increased from zero, right? It's still lower, it's much lower, it's not quite as fast as HI, but it's non-zero now. If you let a little bit more time go, the concentration of HI continues to fall as it of H2 and I2 continues to fall as it becomes hydroiodic acid, and the concentration of hydroiodic acid continues to rise. All right? And now you can see what's happening with this trend. This is going to continue where the forward reaction rate continues to fall, the reverse reaction rate continues to rise until that magic moment when the two are the same. And once they're the same, they will never again change. Doesn't matter how long you leave it, or how often you check. Once the rate of the forward reaction equals the rate of the reverse reaction, they'll never again change. They will always be equal, right? And that moment, sorry, that was a little sloppy. Draw better asymptoting lines. That moment when that first happens, right here, this is where the forward reaction rate equal to the reverse reaction rate. And this is known as, so starting from right here, this is called chemical equilibrium. All right, this is also referred to as the equilibrium condition when the forward rate and the reverse rate are equal to each other. That is the equilibrium condition. All right, and every reversible reaction will get there eventually, where the forward rate and the reverse rate are the same, become the same. All right. Now, probably the most important feature of any chemical equilibrium, the thing that gives you the most information, most useful piece of information, is something called the equilibrium constant. Every equilibrium has one. It is symbolized with a capital K, sometimes with a little EQ not substituted, subscripted there. That is the equilibrium constant, KEQ. And it every equilibrium has one, and it tells you the relative concentrations of products versus reactants once the equilibrium condition has been met, once chemical equilibrium has been established. All right. Now, you can express the equilibrium constant mathematically based on the reversible reaction, the balanced chemical equation for the reversible reaction. So, if you have a chemical equation where A and B are reacting reversibly to form C and D, I can write an expression for the chemical equilibrium. Now, before I do, I just want to point out that the lowercase letters right here these are all stoichiometric coefficients. All right, so those are the numbers in your balanced chemical equation that balance them. Whereas A and B are our reactants, and C and D, capital C and capital D, are our products. All right, now the equilibrium constant, the expression for the equilibrium constant is KQ is equal to the molarity of C raised to the power of C times the molarity of D raised to the power of D over the molarity of A raised to the power of A times the molarity of B raised to the power of B. So you can see that your stoichiometric coefficients in the balanced chemical equation become the exponents. And you can also see that the reactants are in the denominator, and the products are in the numerator. One last thing that I want to mention here is these square brackets mean something specific. When you see something in square brackets, that means molarity of C. That's what C in square brackets means. So anytime you see that square bracket, it's not just a parentheses. They're saying molarity goes here. That's the definition. So it's basically the way to think about it is when we're talking about equilibrium constants, generically speaking, KEQ is going to be equal to the concentration of your products, the molarity of your products, over the concentration or molarity of your reactants. And something that's very important to note, and again, we'll put this into practice in just a minute here, but note you only include aqueous, the aqueous phase, and the gas phase in KEQ. The reason for this is solids and liquids do not have variable volumes, which means their concentrations are constant. So you do not include solids or liquids in the mathematical expression for equilibrium constants. All right, and that is because their volumes don't change appreciably, which means their concentrations are constant. So they don't affect the value of the equilibrium constant. All right, now, finally, here in the last 10 minutes of lecture, we're going to do our first few examples. So this is definitely a concept-heavy lecture. Our next lecture on Tuesday, we'll have a lot more examples. We'll dig into it. We'll apply this more, but we're going to end with a few. So write the mathematical expression of the equilibrium constant for the following chemical equilibrium. And the equilibrium in question is two moles of NO gas decomposing reversibly into nitrogen gas and oxygen gas. Now, the thing you always want to keep in mind is that your equilibrium constant is products over reactants. All right, so we do concentration of products over concentration of reactants. So KEQ is going to be, we'll worry about our exponents in a moment, but first, we're going to put our products. So we have two products, both are in the gas phase, so we include both of them. N2 times the concentration of O2 over concentration of NO. So there's our products over reactants. Now we have to place our exponents. Nitrogen has a stoichiometric coefficient of 1, as does oxygen. NO, nitrous oxide, has a stoichiometric coefficient of 2, so that should be squared. Rocks, great catch. It totally should be O2. Awesome job. All right, so this is the chemical equilibrium, the mathematical expression for the chemical equilibrium for this reversible reaction. All right, let's do another one. Same type of problem. We're going to write the mathematical expression for this equilibrium. So we have aqueous silver nitrate reacting with calcium chloride, also aqueous, to produce calcium calcium nitrate, and silver chloride. All right. Excuse me. Okay, so again, our equilibrium constant is reactants over products. Now our reactants here are calcium nitrate and silver chloride. However, silver chloride is a solid, and so it is not included. We only include aqueous compounds or aqueous substances and gaseous substances. We do not include solids or liquids in the equilibrium constant. So in our numerator, we only have calcium nitrate. In our denominator, we have both silver nitrate and calcium chloride. All right, now for our exponents, calcium nitrate has a stoichiometric coefficient of 1, calcium chloride has a stoichiometric coefficient of 1, and silver nitrate has a stoichiometric coefficient of 2, so we're going to square silver nitrate. All right. All right. And I think this is where I'm going to wrap lecture up for tonight. We'll continue with more discussion, more conversation about chemical equilibrium, more examples with equilibrium constants. We'll even do some math next lecture. How does that sound? But for now, we're going to call it a night. Thank you all for coming. I'm going to stay on I'm gonna close this stream down and then launch a lab stream, just so that this will be nice and concise. But lab normally runs till 9:55, so I'm gonna stay on for another hour. If you have any questions about anything whatsoever, totally hit me up. All right, dudes. I will. For any who want to hang out, I'm still gonna be here, but I'm just closing this stream down and launching a different stream.